Hello everyone and welcome back to this next lecture in the DC to DC converter series, and with this we will be winding up the converter series as well. So in this last lecture we will be analyzing the results of the forward converter. So we had run the simulation last time and I had let the simulation run for quite a while, so we should see some results. So as before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length video lecture series and courses on the MOOC website Udemy and several others. To know about them, go over to the site pythonpowerelectronics.com. That's basically pythonpowerelectronics.com, and go over to the Learn button. In the Learn button, these are the list of courses which I currently have. So if you look at them, there are several. The most basic course is simulating power electronic circuits using Python, in which I talk about the basics of how you can simulate any circuit using Python and Python Power Electronics. And this course is hosted on the MOOC website Udemy. The next course is more on signal processing, and this talks about how we can design and analyze filters using Python. The third course is simulation of magnetics for power electronics using Python, and in this I talk about you can model magnetic components like inductors, coupled inductors and transformers using Python and Python Power Electronics. The latest course which I have which is called Control Analysis with Python for grid connected converters, and in this I talk about how you can use Python for analyzing and designing control systems with a specific case of a single phase grid connected converter connected to a single phase grid. And I have one more free course which is called Why Specialize in Power Electronics, and this talks about the challenges and opportunities that are available in power electronics for any young engineer if you want to know which domain you want to specialize in. So all these courses are hosted on the MOOC website Udemy. You can find the links for these courses in the description for this video. So if you're interested, please do check out the description for this video. So with this, I'll get back to the lecture. So in this lecture, we are now going to create some plots. We've already run it. I'm not going to click on the run button again. So all I have to do is now add some plots. So the first thing is, let's decide what we want to plot. So let's go over to the circuit and let's look at our voltage source. So this is the input. So the input has this voltmeter source, which is the input voltage. So that's definitely something we can plot. And then after that, let's go over to the output. So the output is here in the secondary load. This voltmeter load is the output at the winding 2 of the transformer. So this is the out voltage directly at the secondary terminals or secondary winding at the transformer. Okay, this is not the total, this is not the final voltage across which is available to the load, because remember we are connecting a buck filter across it. So we are connecting a buck filter between the transformer secondary and the load. So therefore this buck filter smoothens out the switching voltage that are available at the output of the secondary of the transformer, and provides a more smoother voltage to the load. So that buck filter, if we can have a look at it, is just a simple LC filter, and of course it has a diode because we want a DC voltage at the output and we cannot have it working during both cycles. And this capacitor here, which is labeled Cout, maintains a smooth voltage across the final resistor load, which is the load resistor. So what we would like to see, of course, is that voltmeter load as well as this voltmeter filter, right? So these will be the final voltages that we are interested in. Additionally, we can, if we want, also plot all these voltages as well. So we can plot voltmeter winding 1, voltmeter winding 2 and voltmeter winding 3. Right? These are the 3 winding voltages which are available at across the windings of the transformer. So we can plot these as well. So let's start with our first plots. So I'll call the first one converter voltages. And let's start adding them. So the first one, as I said, is voltmeter source. This is the input voltage. So I'll call this Vin. And the next one will be the voltmeter load, but it's important to note this is not the final voltage. So I will call this V secondary, right? That is the voltage across the secondary. And the last will be volt filter. voltmeter filter, because this is the final voltage across the filter capacitor, which is now made available to the load resistor. So let me call this VO and save the waveform. So we now have 3 voltages here. So let's click on done, and we can now plot this. So let's go to the file browser and check out our plot. Don't see one. Let me go back, and here we have it. We might have to zoom in. That's not a problem. So let's have a look. So the blue line is the input voltage, and that's a constant 24 volt because we have chosen like a 24 volt battery. The VO, V secondary, which is this orange line, is the voltage across the transformer. Right? This is the transformer winding voltage. So here you see we see a switched voltage, and the switched voltage is only obvious because after all, this is the voltage immediately at the winding, which means that it is actually receiving a switched voltage from the input and the switch, and is producing at the output another switched voltage. So this is only understandable. To know how these different cycles work, we will have to zoom in a little. But the most important is the output voltage, and you see the output voltage seems to have settled to some kind of a DC value, however with some amount of ripple. Right? So this shows that we have produced at the output voltage, or rather at the load terminal, a DC voltage with some amount of fluctuations. Now how much the fluctuations are and how we can reduce the fluctuations is something to do with designing the filter. We might have to increase the capacitor filter, we might have to increase an inductor or something else. That's different, right? But the important thing is this is now a working converter where we have taken 24 volts and we are producing a much lower voltage at the secondary. And this is only understandable because if you look at our transformer, you see that we are choosing a 2:1 transformer anyway. So we are choosing a 24 by 12 volt transformer, and if we have a look at it, this is even lower than 12 volts for the simple reason that we are only switching it at a modulation ratio of 0.3 or duty cycle of 0.3. If you look at our gate signal, we've chosen a constant duty cycle of 0.3. So this shows that we now have a working transformer model, as even if we chose something close to 1, we would get something close to 12 volts. Now we are lower than even 12 volts. So now to know what's actually happening, let's zoom in under some kind of a cycle. So for example, I would zoom in between 0.008 and 0.010. And we might have to do an Y zoom as well because it is all these fluctuations. Let's zoom in between -25 and 30. So the start should be the lower value always, and the stop should be 30. So let's go over to the file browser and check it out again. And this is the result. So let's see what's happening. So for example, we now have blown it up between this 1 or 2 cycles, you can say, of the switching, of the converter switching. So let's look at what's happening. There is a time for which we see that the converter, or rather this secondary voltage, is high. And this will happen when the switch is closed. So for example, if you go to our circuit, when this switch S1 is closed, this voltage source appears across the winding 1. And if it appears across winding 1, this voltage will also appear across winding 2. And that's what we are seeing here. We are seeing that when the switch is closed, we are applying the voltage that is available at the primary to the secondary, but with the turns ratio, because we have a 2:1 turns ratio. So even though 24 volts is the battery voltage and available at the primary, we are producing at the secondary only half of that, which is 12 volts, right? Because we have a 24 by 12 volt transformer ratio, especially with the winding 1 and winding 2. Now, once this switch is open, in that case, now you see that the voltage across the secondary has turned negative. Now the question is, why is that so? Let's have a look. If we look at this once the switch is closed, right, the input, or rather winding 1, does not have any voltage at all, at least from this source, right? But remember, as I already said, the idea behind this 3-winding transformer, let me come over here, 3-winding transformer, is that you do not want to disrupt the magnetic field or the magnetizing current in the transformer, which means the current has to continue to flow. So even if there is no input from the battery to winding 1 of the transformer, we have connected this winding 3 to ensure that that current does not get disturbed. So therefore this winding 3 now acts as a freewheeling path. Now, as you already know, this winding 3 has a dot polarity that is reverse to winding 1 and winding 2. In the case of winding 1 and winding 2, the dot polarity is on the upper terminals. But in the case of winding 3, the dot polarity is at the bottom terminal. So when switch is off, in that case, this winding now supplies current back to the DC input. And if that is the case, then in that case, because of the dot polarity, we are going to have a negative voltage at both these terminals. A negative voltage. So what that means is, across winding 1 and winding 2, we will expect to see a negative voltage. And let's go and have a look. We see that this negative voltage, let me look at the code again. We see that V1 rated and V2 rated are the same. So therefore, we expect that because winding 3 will be producing a 24 volt because of the 2:1 ratio, again winding 2 has 12 volts, but this time negative 12 volts. Why? Because winding 3 is conducting, or rather is supplying energy back to the DC input. Because of the dot polarity, we have a reverse voltage across winding 3. So, or rather winding 2. So now if you look, you see that because of this, the diode will not conduct. If you look at this buck filter, because a negative voltage is available at winding 2, this diode will be reverse biased, and therefore this load will not receive any power from the DC battery. All that is happening is that the transformer is freewheeling and supplying power back to the DC input. Right? Now, if you look, there is a time for which it is negative, and then it starts to decrease back to 0. Now, you might ask, what exactly is happening here? Well, what is happening here is that the current flows only for a certain amount of time. Once the current decays to 0, in that case, this voltage is now no longer, or rather this transformer is no longer connected at all. Right? Because remember, the diode stops conducting once the current flows to 0, or rather the current drops to 0. The switch is already disconnected. So which means this transformer is now completely unconnected to anything. And therefore, this fall to 0 is basically a decay to 0 of the voltmeter, or rather these winding voltages, which finally collapse to 0. Right? Now, let's go and have a look now at the currents, because now that we've seen the voltages, let's map it with the currents. Now, let's go and have a look at which currents we want to plot. So, this is the voltage source. We have the source current, which we can use. And we now can go and have a look at whatever we have. In the buck filter, we have ammeter L1. This is the current which is at the output of the transformer. So this is basically winding, this is the current at winding 2, right? Now, besides this current at winding 2, we need something at winding 3 as well. So let's look at the transformer. Actually, we need voltage source. Here I do realize I made a mistake. I should have put an ammeter here so that I can measure the current in this freewheel path. So the only thing we can now do to remedy this, at least now is I can think of, is we can actually measure this current here, ammeter winding 3. Now, as you might already know, because the dot polarity of this winding is such that the dot polarity is the lower terminal, this ammeter has a polarity in the upward direction, which means that the positive polarity is towards the upper term. This is something you can confirm on your own. So we can directly use this ammeter because this ammeter is measuring the current which is being fed back in the freewheel path. So let's add these. So let's go to our web browser, create a new plot and call this currents. So the first one, as I already said, is we will take ammeter SRC, and this is input. So I'll just call it IN. And the second one is ammeter L1, because as we saw, this is the current at the output of the transformer or the secondary of the transformer. So let us call this I2. And the last one we saw is already ammeter winding 3 transformer 1. So this is the current in the winding, which we know is the same as the current which is being fed back to the input source. So let's call this I3. So with this we are done, and we can click on this as well. So we might have to zoom in. So let's go to the file browser. So these are the currents. So we see that we have a few cycles of this, right? We have the input voltage, we have the secondary voltage of the I2 and a secondary current, and we have the current in the tertiary or third winding. So quite obviously we do need to zoom in. So I would zoom in between the same limit, that is 0.008 and 0.0010. I think we don't need a Y zoom. It seems fairly constrained. So let's go back to the file browser and have a look. So these are the converter currents. So let's place it here along with the converter voltages. And let's say that we have a comparison. So as I already said, that good part is we've zoomed in at the same cycle. So let's come back here. We saw already that when this voltage is high, right, or you can look at this voltage is high, it means that the switch is turned on, right? If the switch is turned on, we are looking at the input supplying power to the transformer. So you see that the green current here is indeed, or rather blue current is rising, because this is the time when the battery is supplying power to the load through winding 1 and winding 2. Winding 3 plays no part at all, and that's where you see here the current in winding 3 is 0, right? The current in winding 3 is 0 because it plays no part at all in this entire thing. It may seem like a little negative, but that's just more of a plotting issue. Now the next part is the question again, what happens at the secondary? Because the primary is supplying current, right, or winding 1 is supplying current and the input is supplying current, this input, this current is also being fed to the load, right? And quite obviously, because there is this switched voltage, this voltage causes the current in both the winding 1 and winding 2 to increase, right? So you see that the orange or the yellow line is also increasing, right? Now the switch is turned off here. When the switch is turned off, now winding 3 kicks in. The reason is because why? The energy in the transformer now has to freewheel through winding 3 and the diode. And now you see the blue line which we saw here, right? This blue line has become negative. The reason is now the battery is receiving power from the third winding. And now if you look at this green winding, green line here, that is I3, this green line is positive. The reason, winding 3 is now freewheeling the magnetic energy stored in the transformer back to the battery supply. So now current flowing into the battery is negative, flowing from the battery is negative, which means current is flowing into the battery, while current flowing from the tertiary winding is now positive, right? And you can see these two are roughly equal to each other. Now the question is, you see here that this current decays to zero, because remember, the energy is eventually dissipating, which means it is dissipating back to the battery, which means the battery is absorbing this power, and therefore as the energy decays, finally the current will decay to zero, right? When it decays to zero, we see that the diode turns off, the switch is already off, and therefore all currents are zero. And you can look at this also, the currents are all zero. When these currents are all zero, this transformer, as we said, is completely isolated, right? That's what essentially happens. This transformer is completely isolated. So we now see that this is pretty much what we were expecting in terms of operation, that this tertiary winding is now responsible for freewheeling the energy stored in the transformer. Alright, now if we go and have a look at this transformer, we will see that there is of course this main issue is here. If you have a look, see, if we have a look at this, we will see that we are looking at this transformer. The main thing was this dot polarity, and this dot polarity is what enabled us to ensure that this transformer supplied current back to the DC battery when the switch is turned off, right? So you can play around with this and verify for yourself what happens if this dot polarity was above, that no effect would happen. Why? Because in that case, this winding would now not conduct when the switch is turned off because of this dot polarity. And this is something that you can try for yourself, right? The only other issue that seems like something a mystery is the reason for this voltage kind of not becoming zero, because you would expect this voltage to immediately become zero. But remember, this voltage here, right, this voltage here is the voltage across the filter, right? And this voltage here is the secondary voltage, which is the voltage at the transformer, right? So remember that there is some kind of cross coupling between all of them as they decay to zero, because remember, the current also, this voltage also is decaying to zero through other means as well, right? So I would say that if, for the sake of completion, let us plot the transformer winding voltages. And we already have this, so let's start the plot. And I will call this voltmeter winding transformer, that is winding 1, call it V1, save the waveform, winding 2, call it V2, and winding 3, call it V3. We click on done. Let's plot it once and then we can zoom in. So let's go over to the file browser, and these are the winding voltages. So again, little difficult to decipher here, so let's zoom in between 0.008 and 0.010. Now remember, all these fluctuations also have to depend on the frequency of operation and also the integration time step. This will improve as you decrease the integration time step, because now you can solve these transitions also a little better. So let's zoom in. And let me just look at it again to know what the Y zoom should be. The Y zoom can be, I think, minus 30 to 30. And there should be one more. So minus 30 to 30. So let's go to the file browser. And let's look at these zoomed in voltages. So here we look at it again. So you see here that we are seeing pretty much the same very much the same pattern in all three. The reason is because winding 1 and winding 3 are 24 volt windings. So for example, if we go to our code, we've chosen winding 1 and winding 3 to have the same rating, which is 24 volts. And that's the reason why you see here that this does seem to superimpose, right? It is winding 2 that is half the voltage, right? Now, later when you come back here, as I already said, when the switch is turned on, we have a switched voltage, and this winding 1 and winding 3 are both 24 volts. And winding 2 is 12 volts. It's important to note that even though winding 3 is 24 volts, it's completely useless because of the polarity of the voltage and the polarity of the diode. The diode will not allow this to conduct. Only when the switch is turned off that this now reverses. And this reversal happens because of winding 3. And now winding 3 drives voltage in winding 1 as well, negative, right? And also at the same time through winding 2. Right. Now here, of course, this is that stage where this is freewheeling. So there is energy supplied back to the input. Once this diode stops conducting, that is when this voltage now begins to decay to zero. This decay to zero occurs largely because we have certain additional components which are connected. So for example, we have connected a parallel resistance, we have connected some capacitors, we have connected some of these, right? Even if we look at our voltage source, we see that they do have some additional components which are connected, probably transformer. We do have some additional components which are connected, and therefore the voltage will not directly drop to zero, but will actually drop to zero gradually as these resistances decay completely the energy which is being absorbed. So now this shows we now have a working forward converter. Of course, it's important to note that there is no control. This is open loop. I've chosen a constant duty ratio. However, you are always welcome to include your own control into this if you choose to, right? You just have to choose another control voltage and feed the modulation signal or the duty ratio to this particular input. That should do it. So with this, we will now end this DC-DC converter series and the forward converter series. And the next week, I will not start with another DC-DC converter, but rather I will look for another topic. There will probably be applications or maybe papers, whichever. Something new other than just basic converters. So as before, if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will choose another topic altogether. So thank you so much for watching and see you soon. Goodbye for now.